Hello, today's topic is integration by trigonometric substitution. So previously we've seen integration by substitution, and this is somewhat similar. There's a slight difference. When we were doing substitution, we tended to take u being a function of x and plug in. Here we're going to actually take x to be a function of theta, since we're talking about trigonometry, and we're going to integrate that way. We will still have to apply the rule you may recall previously from substitutions. We replaced an x with a u. We certainly needed a du instead of a dx at the end, and this will be similar. If we're replacing an x with a theta, we'll need a d theta at the end. Okay, so we'll start with an example. And this doesn't look a particularly challenging integral, but the regular substitution doesn't really work. There's nothing outside this square root to help us cancel. We can't say u equals x squared or anything like that. So we're going to have to apply a different method, and sure enough it's going to be a trigonometrical substitution. Okay, so we've dropped the limits of integration for a second. We'll plug those back in later. And first of all, we'll notice this. So you may be familiar with hopefully you're familiar with the trig identity sine squared plus cosine squared equals 1. So we multiply by 4, this still holds true. And we can rearrange this slightly, so we subtract the 4 sine squared to the right hand side, and we have an identity there. And the substitution we're going to use is going to be x equals 2 sine theta. Now at this point it's not quite clear where this comes from, but we will see in a while how we choose these substitutions. And so if we set x equals 2 sine theta, we know that dx d theta is 2 cosine theta, and another way of saying that is dx equals 2 cosine theta d theta. Okay, and this is going to help us replace the dx here. Recall we're not allowed to have a dx if we're going to have a function of theta. So we can replace the dx with a d theta with an additional term. Okay, so plugging these in, so we replace the x with 2 sine theta, we replace the dx with this term, and this is going to be our integral. Okay, so we'll just start a new page with that there. And at this point we're going to have to do a little bit of algebra on this. You'll notice we have a 4 in both terms here, so we can factor that out. Also, you'll notice we just go back, we get 1 minus sine squared. Well, 1 minus sine squared is cosine squared. That's a trig identity we had. So we have square root of 4 cosine squared here. And sure enough, that's just 2 cosine. We do need the absolute value, just to be careful there. And then we still have another 2 cosine here. So if we combine that all together, we're going to get 4 cosine squared theta. Now it's still not quite in a position where we can integrate it. We need one more trig identity. And again, this is hopefully a trig identity you're familiar with. It's the double angle identity. And this gives us that our integral becomes 2, and then the quantity 1 plus cosine 2 theta, which we now can integrate. So obviously the 1 just integrates to theta. Cosine 2 theta integrates to sine 2 theta over 2. Like a little mini substitution there. And that's our integral. We're still in terms of theta. Okay, so we can put the limits in here. Recall our substitution was x equals 2 sine theta. And so you can pretty quickly solve that if x equals negative 2, theta would be negative pi over 2. And if x is 2, it would be pi over 2. So our limits become negative pi over 2 to pi over 2. And we have these terms, which of course we just integrated a second ago to get to this. And now because we have the limits, we can plug them in like so, and we get 2 pi. And you might think, well, why did we even bother with limits? Why didn't we just leave that example without the limits? Well, this will help us check this. Square root of a constant minus an x squared, this is actually a semicircle. It's the top half of a circle. Its radius is 2. So a circle of radius 2 has an area of 4 pi. Therefore, a semicircle of radius 2 has an area of 2 pi. So sure enough, this is correct. Now, obviously, most examples won't be as simple to check as that, but that does give us a check that maybe we've done the right thing here. Okay, so I mentioned how do we decide what the substitution should be. And we're going to look at 3 possible types, all with these square roots. And the first type is if we have the integral of the square root of a constant minus an x squared. And that's the example we just had. So we have this a squared minus x squared inside a square root. We're going to use x equals a sine theta. And if you recall the example we just saw, we had 4 minus x squared, so we should have 2 sine theta. If we have an x squared plus a constant, so we have x squared plus a squared inside a square root, we're going to use x equals a tan theta. And if we have the square root of x squared minus a squared, so x squared minus a constant, we're going to use x equals a secant theta. Okay, so those are the three types we have. And it'd be good to have this sort of handy when you're doing these questions to know which ones you should use. We're also going to need a few trig identities. These are some of the squared identities. So sine squared plus cosine squared equals 1, most people are familiar with and happy with. If you can't remember these next two, they actually just derived from the first one pretty easily. This one is just the top identity divided by sine squared. And this one is just the top identity divided by cosine squared. So you can always derive them that way if you can't remember them. We'll also have a couple of double angle identities. I wouldn't claim these are all the identities we'll need, but there's certainly quite a lot here that we can use. Again, maybe having a table of trig identities handy would help as you're doing these things. Okay, so let's take another example. Okay, so now we'll see we have this term. We have the square root of an x squared plus 9, in other words, x squared plus a constant. And so what we saw from our table is that this should be a tan type. And sure enough, we have x equals 3 tan theta. Remember, it's the square root of this 9 here, the constant in front. And again, we need to get rid of the dx. So dx d theta is 3 secant theta, secant squared theta, excuse me. So dx is 3 secant squared theta d theta. Okay, so we have the x that we can substitute in, we have the dx we can substitute in, so let's throw all those in there. So obviously we're squaring the x's in both places, so it's 9 tan squared, both here and here. And we replace the dx with a 3 secant squared theta, and that's our integral. Okay, so there's still obviously lots of algebra to do to simplify this so we can get it in the place where we can integrate it. Well, first we can factor the 9 out inside the square root, and if we factor the 9 out inside the square root, it becomes a 3 outside the square root. Now we have lots of constant terms. We have a 3, a 3, and a 9. We also have tan squared plus 1. So we cancel the 3's, bring the 9 outside. Tan squared plus 1 is secant squared. But of course that's inside a square root. So if we cancel all that, we get here, and we'll just go back to see how that worked. Here we have secant squared. Here this is really just a secant. So we should just get a secant on top, and sure enough it's that. Okay, well, still not quite sure how to integrate it. Remember, tan squared is sine squared over cosine squared. But because the tan squared is in the denominator here, we'll sort of flip that. So we're going to get cosine squared over sine squared. Secant is 1 over cosine. We can cancel the cosine squared with the cosine. So we just get cosine theta over sine squared theta d theta, with a 1/9 outside. Okay, well, how are we going to do this? Okay, let's give ourselves a clean page. And hopefully, from what we saw in regular substitution a couple of classes ago, we might know how to do this. And in fact, if we set u equals sine theta, we can see we have the cosine top. So we set u equals sine theta and du equals cosine theta d theta. That looks actually like a pretty simple integral now. Okay, the cosine theta d theta disappears with the du. So we just get 1 over u squared du. And finally, we're in a position where we can integrate. Okay, we can make the power u to the negative 2, and we can actually integrate this. Notice at this point we've done lots of work, but we've not actually integrated yet. We still have the du here. So let's integrate. And that particular step, of course, was very easy. We get 1/9 of negative u to the negative 1, plus the constant to integration. And of course, because we know that u is sine theta, we get minus 1 over 9 sine theta plus c. Okay, we're good. Except, recall our initial integral was this. It involved x's, and our answer seemed to involve thetas. I guess we could go back and take arctans and things, but that's going to be kind of ugly. So what we're going to do is this. Remember we said that x equals 3 tan theta. That was our original substitution. And we can rewrite that as x over 3 equals tan theta. Okay, just a quick division by 3. And let's think about that as a triangle. Right? If we have the angle theta, we know that tangent is opposite over adjacent, so we're bringing a triangle in that represents this. And not only, of course, do we know the opposite and adjacent, Pythagoras tells us that we know what the hypotenuse is. We know that the triangle looks like this. Okay, well, if we know the triangle looks like this, then we also know what sine is. Okay, based on this triangle, sine is opposite over hypotenuse, so that would be x over x squared plus 9. And that's going to help us substitute back into here for what sine is. Now notice the sign's on the bottom here, on the denominator of the fraction, so we'll have to flip it just a little bit. So we get minus 1 over 9 sine theta plus c. It's minus the square root of x squared plus 9 over 9x. As I say, we just kind of flipped this fraction because the sign within the denominator. And we still have the constant of integration. And sure enough, that is the integral. Okay, we've solved this integral to here. If you're not quite sure, you can always do a check by differentiating back again. There's a little bit of chain rule, a little bit of maybe quotient rule there to check, but you can check that. And that's the technique we're going to use. Okay, I say this triangle method is quite useful for getting our answer back into x's. And maybe just a quick reminder, these are the 3 types that you're going to use. Okay, and that is integration by trigonometric substitution.